So if you're not in our Discord channel, I have something to show you. I found Shrek 2 on VCR. I actually found it a while ago, but still, that's incredible. So what I wanted to talk about today, sorry that I haven't made a video in a while, like I said before, I've been really busy. But this is something that's caught my attention that I felt like I really needed to discuss because I find it super interesting. And that's Roger Penrose's theory of quantum consciousness. Now, it's a very big theory, and it doesn't just involve Penrose. He collaborated with, let me check the name, Dr. Stuart Hameroff, to actually come up with the theory. And there's some things about it that are quite appealing, and that can actually go a long way to explaining the nature of consciousness. And if not, how consciousness itself happens, perhaps, its function. Even if the theory ends up being wrong about the how consciousness actually arises, it could be right in how it functions. And by that, I mean how it actually kind of enables free will. I will be injecting some of my own thoughts in here, but keep in mind that I'm trying to kind of explain a theory that is very difficult to explain. Now, to start off, I guess the fact that consciousness itself, consciousness exists, and again, you can either mean consciousness or just sentience or qualia, subjective experience, the fact of being and the fact of, having an experience and experiencing colors and sounds and pain and all sorts of sensations, that actual fundamental experience. It's still very mysterious and we don't know how it arises, which is, led to the positing of the possibility that it involves some, it goes beyond classical mechanics, and that, if we go beyond classical mechanics, we can actually explain what consciousness is, which is why you hear this theory of quantum consciousness. Now, that may sound very, mystical and woo-woo, but it does make a lot of sense that something as mysterious as consciousness would arise from something as mysterious as quantum mechanics, because the two actually have a lot in common. Both seem to involve a loss of information. In quantum mechanics, there's always this missing information. You'll understand what I mean by information when I get to it. But in studying consciousness, there's also this kind of missing information. There's this missing information in the explanatory gap. If you don't know what the explanatory gap is, it's the fact that I can't actually confirm that my experience of, for example, the color green is the same experience as your color green. Every time you look at a green object, from my perspective, it might look completely different than what you experience. And I can't, there's no language I can use to actually explain what my experience is like. I just say green and you say green, and we just hope that we're both seeing the same thing. But there's a chance that we're not. That's the explanatory gap. And there's also this kind of gap in quantum mechanics. And it's a gap that's built into quantum mechanics. And you can see right there's kind of a relation there. So, by the way, I'm already 3 minutes in, but this explanation is going to be quite difficult. It's difficult enough for me to grasp it. And also, I'm not confident in my ability to properly explain it. So if I do a bad job of explaining it, that's to be expected, because I am talking about things that are really, really out there and really conceptual, really difficult to conceptualize. I will leave a lot of links in the description that supplement this video. One of Veritasium's videos about computing is really, really useful for what I'm talking about now. So I'll link it in the description. And by the way, if I promise to link something in the description and I forget to do it, please leave a comment to remind me, because I'm very careless. But what this relates to is a kind of idea in mathematics, which is the incompleteness theorem. Now, I haven't talked a lot about math on this channel. I want to. I'm making a video about rationality that should come out soon, that will explain basically the fundamentals of math. But math is always a system. And it's always a system which kind of you construct these basic rules, and then you kind of see what results as a result of those rules. So, for example, you can prove many mathematical statements by kind of following the logic of these very rigid rules. So, for example, a plus b must equal b plus a. You can move around things in multiplication, but you can't do that in division. And that's what kind of gives you these rigid rules that you can follow, and then kind of follow the logic to their conclusions. And so there are many mathematical statements that you can prove by kind of assuming a system and then following the system to its conclusions. I'll start with, the most simple one, because you might imagine that, we decide as humans that 1 plus 1 equals 2, and that's how we know 1 plus 1 equals 2. So, again, math is this kind of world where we decide these, fundamental axioms, things that we take to be definitely true, and then just see what happens if we hold these statements to be true, what will happen as a result of that. And you can actually systematize math very well. And you can kind of create rigid rules that will eventually lead you to the statement 1 + 1 = 2. You can create a whole bunch of kind of very fundamental axioms. For example, the axiom that the successor of a number equals the successor of that same number. If that rule holds, and then other rules also hold, you come to the inevitable conclusion that 1 + 1 = 2. And then you can come to other conclusions if you just keep following the system. For example, you can prove that the square root of 2 is irrational. So an irrational number, for example, like the square root of 2, never ends. So it starts as 1.4 and then just goes on forever, and it never ends. It'll just keep going on forever, which itself is a mind-blowing concept, and really kind of mind-blowing that humans even conceptualize that in the first place. But you can prove that this is true, and the reason and the way you prove it is that you assume that it is rational. So a rational number can be written as a fraction, and then you kind of just follow these logical deductions and realize that that can't be true. Therefore, it must be irrational. So you can prove a lot of things in mathematics using kind of a system that you build, and you can just call your system anything. So we'll just call the system R. And again, R is just a basic mathematical system, and there's a lot of mathematical systems. In fact, the basic arithmetic that you learn operates under a certain system, but then something like topology is a different system. So it's like a different set of rules. So it's like topology has to do with objects. And there are certain rules about manipulating those objects. You're not allowed to shear things. You're not allowed to like pull things apart. And then you kind of just follow the logic to its conclusions and see what statements are true given those kind of initial conditions. And again, there's a lot of like systems, that you can build. For example, non-Euclidean geometry. So like most of the time we assume that geometry in the real world is Euclidean, but then you can develop a system of non-Euclidean geometry and then discover what's true there. So you might know, for instance, that a triangle, no matter what kind of triangle you draw, if you add up the internal angles, it'll always have 180 degrees if you add them all up. That's not true in non-Euclidean geometry. If you operate in a different geometry, under different rules, you actually get a different conclusion, that triangles can have angles that add up to more than 180 or less than 180. So again, a different set of rules, and you get kind of these different kind of logical deductions result from them. And that's basically the essence of rationality. I'll discuss that next video. But in this video, I just wanted to talk about the notion of the incompleteness theorem. So the incompleteness theorem is actually pretty interesting. And I'll leave that Veritasium video for you. The video itself is, it's much better than I can probably explain it. One of the kind of limitations I have is that because I'm a YouTuber that doesn't really make a lot of money, I don't have money for crazy animations that will actually kind of produce the metaphors that kind of give you the intuitions about this stuff. But, other people do. So I recommend you watch those videos and you'll get a sense of what I'm talking about here. But essentially, the incompleteness theorem states that anytime you make one of these mathematical systems that I've been discussing, there are going to be true statements in that system that you can't actually prove using that system, which is really bizarre. And there's a lot of examples of this. So one of these could be the Collatz conjecture. I'll link another video to it below. But essentially, it's this conjecture about if you do something to every number, it'll just end up. If you do this basically like this algorithm to any number, it'll end up being in this kind of continuous loop. And again, it's just a conjecture. We believe that happens to every number, but thus far nobody has been able to prove it. And it could be that we just haven't found the proof yet, or it could be that it's unprovable. That doesn't mean it isn't true. Unprovable and not true are not the same thing. It could actually be true, just unprovable. So there are true statements that are unprovable. In fact, you can actually write that as a statement. You can write in using mathematical language, this statement cannot be proven. And think about it. This statement cannot be proven. If that's false, that means you can find a proof for it. But if you find a proof for it, that means you've found a proof that it isn't true, which is a contradiction. So your only other option is that it is true. The statement is true. This statement can't be proven is true. But that means you will never be able to find a way to prove that, using that system to actually get to that conclusion, which is rather mind-blowing. And there's a lot of things that it turns out are like this, that they're just non-computable. You can't actually get an algorithm to tell you whether the statement is true or not. And it's kind of remarkable, actually, because it means that the things we can prove, for example, that root 2 is irrational, is almost like a miracle. And the fact that we were able to prove anything in mathematics at all is a miracle, because it turns out there are so many things in math that can't be proven in terms of that system. And now this is actually like a given condition for any system. And now, I know that sounds like super mathematical, and that it might be hard to conceptualize, but even like logical statements, like any set of deductions, will technically have true statements in it that can't be proven with those statements. or with with those rules. And we can take this to the realm of physics. So like in physics, physics is a whole bunch of equations. So for example, I'll put the equation for general relativity on the screen, and you can actually use this this equation to deduce truths about the universe. For example, you can deduce this thing, which is the Schwarzschild metric, and basically this thing, which was derived solely through math, describes a black hole before we ever even discovered a black hole. So we can discover things in the math before we even discover them in reality. Now, I've been discussing like these non-computable processes, but Roger Penrose's theory is fundamentally that consciousness is one of these kind of non-computable things. It results fundamentally from basically a problem that can't be solved using computation. And again, there are a lot of problems like this. It just seems to be that consciousness is also one of them. But what does this have to do with quantum mechanics? Well, there are actually like a lot of things about quantum mechanics that makes it weird, but also a lot of things that make it kind of uncomputable. You can get kind of results, but there's a kind of sense in which you can't calculate anything with certainty in quantum mechanics, and this turns out to be one of these kind of unprovable problems. So quantum mechanics is very complicated. I'm not gonna act like an expert, but I've been like trying to wrap my mind around like the complex physics behind quantum mechanics for like 4 years now. So I kind of get it. It's difficult to understand, but once you wrap your mind around it, you can start to get kind of understand what's going on. So there's a lot going on in quantum mechanics, and there's a bunch of things that I could say. But again, quantum mechanics deals with like the fundamental particles of nature and their kind of weird behavior. And there's a lot of like examples of this weird behavior. So I guess I'll confine myself to a couple examples. The first one I guess I'll talk about is to think about an electron orbiting an atom. The question is, where is this electron? Now, funny enough, we can't actually know where the electron is. Where the electron is governed by the Schrodinger equation, which you can see right here. And when we want to kind of calculate where the electron is, what we get instead is we apply the Born rule, which is we just square this thing. And then what we get is like a probability function. So we get this wave-looking thing, and this describes the probability of where the electron might be. We can't actually tell you where the electron will be. So what happens when we actually try to measure the electron rather than kind of just inputting it into this equation and seeing where it might be? Well, we actually cause the thing to change. So, an electron as it's orbiting an atom doesn't exactly have like a defined position. It's in this state what we call a superposition, where it's kind of in multiple places at once. But when we measure it, it actually kind of is in a place just for, a momentarily. And the reason for this is because the act of measurement itself collapses the wave function. So again, it's in like this, you can almost think of it as like a literal wave around the nucleus of the atom. And when we measure it, that wave collapses and the electron is in a single position. In fact, it has to be, because how else could we see it? But there's a couple things that happen as a result of this. First thing is that by doing that, we've just increased the uncertainty in other properties. So by measuring an electron, basically we're bouncing light off the electron. So we kind of know where it is for a split second, but then its momentum becomes undefined. So there's a sense in which we can't calculate the whole thing with certainty. We can't know all the information at once. But there's also this sense in which we created information. Because, okay, so when we explain what information is essentially anything that can be known. So like where the electron is, that's a bit of information because you can know it. But here's the thing, we can actually kind of create information, because normally in the world, like information is just out there and then we kind of extract it using our sense organs. So for example, this computer is approximately like a foot, this computer monitor is like a foot and a half from me. I can tell that because I can see the distance between me and the computer. So I have information about the computer. But I didn't create the information. The computer is that distance from me and I just measured it. With quantum mechanics, it seems like the act of measurement itself produces the information. And this actually doesn't have anything to do with consciousness, or at least, most physicists don't think it has anything to do with consciousness. There are people who believe that consciousness, causes the universe. And I don't have anything to say on that position because I frankly don't know. But what I do contend is that the other position does make a lot of sense, in that measuring something basically causes it to have temporary value. So you don't know where the electron is in the orbit, but when you measure it, you create its position. You kind of produce that information. And this is called the wave function collapse. Again, it's in like this wavy state, and when you measure it, that wave function collapses and it gives you a definite answer. So it's in this state of probability, you measure it, and then it gives you a definite answer. But then again, that causes uncertainty and other things. The point is that in a sense, measuring the universe causes the universe to be a certain way. It's in like this almost flux state of uncertainty, but when it becomes measured, it's like it kind of gains a measure of certainty. And basically, to kind of summarize what the theory is, it's, I actually not going to go into like microtubules and like all the actual like physical mechanisms. I'll leave that to another time if you're interested. But to get to more like the physics side of things, basically what Penrose is saying is that that wave function collapse is a moment of proto-consciousness, and consciousness itself, even like the fact that we can understand things, is built up from these kind of proto-consciousness moments. That again are a result of the wave function collapsing. Now, how do we make sense of this? Well, there's a lot of ways to actually make sense of it, and a lot of ways that you realize that something like consciousness could actually give us free will. Because think about it. So one of the kind of impediments to free will and the notion of free will is the fact that like the determinism, the universe is fully determined. So like everything that's going to happen in the future will inevitably happen, because all you have to do is look at every particle in the universe and then follow these differential equations, and then you'll see where the universe is going, and then there's no free will. Well, there's a sense in which that isn't actually true, because by interacting with the universe, we change it. So like you don't know where that electron is, but by measuring it, you change it. It's like it's where whatever it was before has been altered, and it's been altered because you measured it, because you've gained information about it. There's another example that actually shows this much more clearly. I guess I'll link a video to the experiment, but it's this double slit experiment, which shows essentially that if you shine photons at a slit, at these kind of small, very small slits. So they're very small, and the photons are very small. And the photons, when it travels in a wave, or at least we think it travels in a wave, and then it passes through these slits, and then it constructively interferes and produces this interference pattern. The thing is, if you fire the laser one photon at a time rather than a bunch of like as a continuous laser, you still get an interference pattern. So, and the reason this is confusing is because if you fire only one photon, it can't go through both slits simultaneously. If you fire like a stream of photons, then some of them can go this way, some of them can go that way, no problem. But if you fire one, it doesn't really make sense, because it has to go through either one or the other, and yet this interference pattern still appears. So what seems to be happening is that, again, it has to do with the fact that as the photon is traveling in the air towards this slit, it's in this state of uncertainty. But the second it hits the wall, it kind of has to pick a position, and then it picks a particular position, and that's where it is. That's its position. But before, its position was uncertain. That's why it's able to go through both slits simultaneously. And that's the kind of insane thing about the world. In fact, everything is built up of quantum mechanics, of quantum particles, so everything is kind of like in this blurry state of quantum uncertainty. But the act of measurement produces a certain state. So what does this have to do with free will? Think about, like, for example, a meteor that's about to hit the world. You might think, like, that's an inevitable thing, so there's nothing we can do about it. Well, what about using our consciousness? So our consciousness does seem to be something, at least related to the collapse of this wave function. So we look out into space and we see this meteor approaching us, but we see it, right? So like something that was kind of in this quantum blur now is in a state of certainty. And this happens all the time. So like look at anything around you and then close your eyes. If you close your eyes, you can kind of roughly think of this as like the universe being in this uncertain state as your eyes are closed. You open your eyes, and then there are photons bouncing into your eyes, and that's kind of causing like the certain position of everything around you. You can extract information from from the universe out there, but there's also a sense in which you're creating that information, and this is how you change the universe. Again, this is why free will might be suggested by this idea, because the universe was in a state of like going as it was and there's no control over it. And I know that sounds kind of weird, like, because again, the intuition is that the universe just as it is and you measuring it doesn't change it. But it seems that you measuring it does it. Even it does change the universe. Even very simple things like looking at objects, in a sense, kind of determines where they are. And again, that's a very microscopic effect, so you might think that's not significant. But let's go back to that meteor example. So the meteor is coming towards you, and what kind of information can you extract from it? Well, you know its position, you know its velocity, you can tell whether it's going to hit the Earth or not. And if you do see that it's going to hit the Earth, you can then do something about it. For example, so whereas a lack of information in the past would have prevented us from doing anything, so in dinosaur times, they didn't know about asteroids or space or physics or gravity, they would not have been able to calculate the trajectory of that object. But by being able to do so, we can do something about it. So we can perhaps calculate its trajectory in 3 days and then fire a missile that, intercepts it at the particular course. So by getting information of the universe, we can kind of redirect its course. And this is exactly what's happening. And again, it's actually one of the interesting things is that this theory is about microtubules and the way they work, and the fact that like these microtubules may contain the structures that collapse the wave function. But even if that's wrong, there's a sense in which there are other mechanisms, the other conceivable mechanisms, which kind of produce this result regardless. And it's very simple. Like let's do a very simple example. Touch an object. So I'm going to touch my desk, and you notice that the desk is pushing back against me. What's going on there? Well, the reason you can't just push your finger through a desk is because the desk has electrons on top of it, and then when you try to push your fingers into the finger into the desk, the electrons on your skin repel it. And this is actually related to Pauli's exclusion principle. Funny enough, Pauli was a friend of Jung, and Jung derived a lot of ideas about synchronicity from him, which are actually really interesting, and we might talk about another time. But what's going on? So in order for the electrons in your skin to repel the electrons in the wood, this is a wooden desk. The positions of both kind of have to be certain because they have to be close to each other to repel each other. But before I touch them, they're kind of in like this uncertainty state, like in this wave function. But then I put my finger there, it's almost like measuring the electrons because their positions have to be certain in order to push back against me. So I'm creating information, and I'm doing that. And not only that, but something in my brain is able to extract that information. So when I look at objects, photons are bouncing into my eyes, and like the positions of those objects are being determined. But simultaneously, there's some experience which allows me to retain a copy of that information and use it. Now, that whole aspect of consciousness is still mysterious. I don't think Penrose actually explained that. He just explained the possibility that it arises from something like this. But yeah, I think that this theory does kind of allow itself for the notion of free will, and it does make a lot of sense as towards the function of consciousness. That consciousness is able to build a map of the external world, extract information from that world, and by extracting information, change the course of the world. So again, that's what consciousness is for. Like if you compare a non-conscious organism to a conscious organism, the conscious organism has this advantage because it's able to kind of produce some kind of map of the external world, and it seems that by producing quantum information, change the world, because the only way to change the world is to produce information. As weird as that sounds, I don't mean change the world in like a hippie sense. I mean like literally change the trajectory of the world, because again, according to determinism, everything is determined, so you can't change anything because it's just going to happen the way it happens. But if you think about quantum mechanics, and again, this is why a lot of people assert that quantum mechanics does allow for free will, and I assert that as well. If you think about quantum mechanics involves the creation of new information. And if you create new information, this implies that the state of the world before that you created that information was uncertain. By making it certain, it's now kind of going to happen in a very particular way, but you can predict that particular way and do something about it. Which is really interesting because, again, if you're not conscious of something, it implies you can't do anything about it. So yeah, it's really interesting. There's a lot of examples of collapsing the wave function, literally. And even something for example, if you think about looking at your chromosomes, so the fact that we're aware of genetics gives us power over genetics. So for example, a lot of people would have died from genetic diseases, but the fact that we know that, we can now prevent those genetic deaths. But this itself is kind of a collapsing of the wave function because we didn't know about chromosomes. They kind of existed in the dark. But by using literal microscopes to see them, we kind of create certainty and kind of understand their structure. And now, because the things are certain, we can kind of derive information from that and use it to our advantage. So yeah, I didn't actually explain the theory very well now that I think about it, but I probably will make a follow-up video to actually explain the physical mechanisms because they're super interesting. I'm still trying to wrap my mind around it. But yeah, I'd like to know if you thought that was interesting and if you thought that was coherent and made a lot of sense. There's a lot of things going on and a lot of concepts that might be new and foreign, but I hope I did a good job of explaining it. And if I didn't, I'll be happy to provide a lot of links and a lot of supplementary information, which goes into this in more detail. Okay, thank you for watching, and I'll see you next time. Peace.